My name's Alison Etheridge. I'm a sort of local here. It is a huge pleasure to introduce Sir Martin Hara of EPFL and Imperial. He doesn't need much introduction. Of course, we all know him as the developer of the Amadeus sound editing software, but he's also apparently done some mathematics on the side, and he deservedly has won a string of prizes for his groundbreaking work in stochastic analysis, notably, of course, the 2014 Fields Medal for his work on regularity structures, and then the, I think, considerably more lucrative Breakthrough Prize in 2021, which is presumably why he can afford to live in Switzerland. He's a man of very many parts and very many languages. And in fact, I reminded him the other day that I once asked him what his first language was, and he doesn't know. French, German. Happily for us, of course, above all, he is superbly fluent in the language of mathematics. I have never failed to enjoy one of Martin's lectures, and I'm sure that today will be no exception. So Martin, please tell us all about Yang-Mills and the mass gap.
Thank you very much. Well, Alison just promised she would embarrass me, and she succeeded. And well, I mean, I'm also sort of embarrassed to be here anyway, even without Alison's introduction, because I'm really much less of an expert on Yang-Mills than people we heard this morning, for example, were experts in their respective subject areas. But I guess the reason is that somehow on that Yang-Mills Millennium problem, I suppose somehow in the first 20 years since 2000, not really much progress has been made. And it has had a little bit of a sort of revival in the last 5 years. And I was somewhat involved in one aspect of that. And I guess that's why I was asked to speak here. And so maybe I should start by actually trying to explain what this Yang-Mills thing is all about. Now my iPad somehow locked itself. Okay, that's fine. So what's the Yang-Mills field theory? So first, what's a field theory, right? So a field theory, by and large, it's basically some kind of functional on a space of field. A space of fields is usually some kind of space of functions. In this particular case, it's actually not really a space of functions, it's a space of connections. You can view it as one forms. So here the setting is, you've got a compact Lie group, think of it as whatever, SON or something. And then you take a principal bundle, but it really means you have some base space, and then you take the direct product of that with your group. Of course, globally, it could have different structure, but let's just look at it locally. So you have some base space, which is going to be some copy of RD. Of course, you could be fancy and it could be a manifold, but let's just pick RD or torus, so we don't have to deal with curvature and stuff. And so you look at the product with that group. So at every point of your space, so you sort of attach a copy of the group. And then you really think of this as attaching a copy of the group, but where you've forgotten which element is the identity element, okay? And so you really just, if you think of the group as U1, which is in the context of Yang-Mills not an interesting group, but for the sake of drawing pictures, it's an interesting one because it's the only one that I can draw on a two-dimensional surface. So you have your sort of base space, right? And then at every point, you sort of attach a copy of U1, which is really just a circle. But now, U1 is not actually a circle, right? U1 is a circle with an identified point, which is the identity element. But now you remove that identified point, right? So you really attach circles at every point. Okay, so you have sort of like at every point of your space, you have kind of a circle. And so now that means that you no longer have a canonical way of lifting, right? Like if you take a path in your actual original space, right? You no longer have a canonical way of lifting it to this bundle where you've attached a circle at every point, because you don't actually have an identified point on this circle anymore, right? And so now if you want to give yourself a way of lifting it, well, you basically have to specify how you glue all of these circles together. Now you could do that globally by, again, just simply choosing one distinguished point for each copy of the circle and decreeing that this one is sort of your identity element, and then you sort of lift it by simply lifting every point to the identity element. But you could also try to do that more locally, right? By basically saying, well, say I'm, here I have that sort of copy attached to it. Now this point, maybe I lift it up to here. And now I have these copies of circles kind of attached, right, to every point down there. And now I have to sort of specify how I'm going to lift that red curve to a green curve. And so at every point, basically, I have to tell you, if everything is smooth, I have to sort of give you a tangent vector up there in the bundle. And if I introduce some coordinate system, right, that really means that I need a map that takes tangent vectors down on the base space and spits out tangent vectors up in the bundle. And I want to do that in a sort of equivariant way, in the sense that all of these circles, well, I still have the group of rotations that acts on them. And of course, in general, you have sort of like the group that acts on itself by multiplication. And so you want to say, well, if, for example, say that same point, I would start by, for example, lifting it here, and then I give myself some kind of tangent vector here. The way these two guys are related is by, just acting with your group of rotation. There's a global action of my group of rotation on this, right? Since at every point I sort of attached a copy of the circle, I can rotate all of them by the same amount. So there's certainly a global action of the group of rotations on this space. And so whenever I'm given a tangent vector, I can always sort of look at the image of that under a global rotation, and I want these things to be kind of compatible, right? And so that basically means that lifting curves is sort of the same as giving myself a way of assigning to every tangent vector downstairs a tangent vector upstairs, but like at every point, but I just really need to specify it only at one point, right? Because at every other point, it's given by just doing a global rotation, right? And then a tangent vector, and it needs to project down, right? It's like I want the lift of my curve to kind of project down to the original curve. So it's certainly in the base space, it needs to point in the same direction. So you really only need to say where it points in the, kind of tangent space of that copy of your group. And of course, the tangent space of a Lie group is just the corresponding Lie algebra, right? So what it means is that here, oh yeah, there's something slightly wrong with this, but it works if I do that. So it means that, so a connection, right? So a connection is basically a way of lifting curves in the way that I've just described. You can essentially describe it as a one form with values in the Lie algebra, right? It's not a canonical way of doing it, because for this, I had to basically already choose a coordinate system. But then, of course, I can change coordinate systems in the sense that I can simply act on each copy of the circle with a rotation, but not necessarily the same rotation for every circle, right? Since I've sort of now decided to forget about where the origin lies, I can kind of rotate any of them independently. I sort of get the same space back. And under that sort of changes of coordinates, well, my one form is going to transform in a certain way, which is not just by conjugation. It's going to transform in a slightly different way. So in that sense, it's not really a one form, right? But it is a one form in the sense that if you fix a coordinate system on the bundle, then it's a thing that takes a tangent vector and spits out an element of the Lie algebra, okay? So that's the fields for Young-Mills theory. And then for field theory, you want first a space of fields. So I've kind of described that to you. And then you want an action, which is basically just something that takes as input a field and spits out the number, usually a positive number, doesn't necessarily have to be. And in this case, it's the L2 norm of the curvature. So what's the curvature? Well, the curvature here, it's kind of, oh, this does the same kind of thing. Okay. So the curvature here at a point is you take, instead of lifting kind of a curve like this, you lift like a tiny circle. Right? So if I lift a tiny circle, then with this local way of doing things, when I lift a little circle, it doesn't necessarily, well, maybe I shouldn't have drawn it like this. It doesn't necessarily close. Right? Like you lift it, it's going to end up on the same copy of the circle here, but it's not necessarily going to end up at the same point. Okay? And then the curvature is the thing that measures, in some sense, that discrepancy, right? Like if we take a little circle of radius epsilon, and you do that, it's going to have a discrepancy that's actually of order epsilon square, and then you take sort of the coefficient in front of the epsilon square thing. And so that's going to be, so that's what I call FA here. If you figure out in coordinates a formula for it, you arrive at this formula here, but it really just does what I just showed you on the picture, right? And so that's a 2 tensor. So it's a thing that now takes as input 2 vectors and spits out an element of the Lie algebra, which is natural here, right? Because in a higher dimensional space, if I want to do a little loop, well, I have to specify the plane in which I do my little loop, right? And so that's basically specified by 2 vectors. And then it's going to be antisymmetric, because if I sort of run the loop the other way around, well, I'm going to do exactly the opposite. And so I'm going to get the negative of what I got the other way around. And now the action functional in the case of Young-Mills is this L2 norm of the curvature tensor. Okay, and so for this, of course, you have to put a norm on that Lie algebra, but if your Lie group is, say, simple and compact, there's a kind of canonical norm on it up to scalar multiples, so you just fix it. Now, okay, so that's a field theory in general. It's you have a space of field and you have an action functional like this. And then the classical field theory, what you typically want to study is either minima or critical points of this action functional, right? So what you would do classically is you take some kind of functional derivative of this action functional, and then you try to look at points where this functional derivative is 0. So you look at some kind of critical points of this action functional. And that's a very interesting problem in the case of Young-Mills. Also, especially, I mean, you can have much more complicated geometric features if your base space is a manifold and your bundle has kind of non-trivial topologies. The critical points of this action functional are very interesting. It's a very interesting field of study, but this is not what I'm going to talk about here. Okay, and this is, in some sense, not only marginally related to the Millennium problem as it's stated, but it's in itself a very important field of study. And so, for example, Karin Uhlenbeck got the Abel Prize in big part thanks to her contributions to that aspect. Now, okay, so as I already mentioned, right, like one thing which is like a special feature of this Young-Mills action functional is that, well, okay, so I told you that you have these coordinate changes where you simply rotate each copy of this group by a certain amount, right? So that gives, there's a big group here, which is the smooth functions, say, from your base space into your Lie group. And then that acts on your space by at every point x, sort of rotating by g of x, right? And then there's a natural way in which these connections transform under these changes of coordinates. And that's given by a formula like this, right? So that's the thing that tells you that even though, I claim here that they are one forms. They are not really one forms because real one forms transform like this. And whereas this thing transforms like a one form, but with this additional term, that, if you do somehow the picture that I showed earlier on, that's what comes out, okay? And that's somehow how connections transform under these changes of coordinates. And now if you do the curvature, well, under these changes of coordinates, the curvature in some sense shouldn't really change. That should be something intrinsic. In fact, it does change a little bit, but it changes just by conjugation locally, okay? So what happens is that if you look at the action of these changes of coordinates on your curvature tensor, that one really transforms like a tensor. This is really a 2 tensor. So it simply gets conjugated by G. And then this norm that we've chosen here, it has the property that if you conjugate an element, if you look, right, you conjugate an element of the Lie algebra by an element of the Lie group, the norm doesn't change, okay? So that means that this action functional here has the property that it's sort of intrinsic, right? Like I can do these change of coordinates, and it doesn't actually change the value of this action functional. Okay. So now, okay, so maybe I don't want to spend too much time. I mean, obviously, this comes from particle physics, right? It comes from elementary particle physics. This Young-Mills theory in general, it was actually introduced in the 50s. And it is basically the theory that you use to describe, the standard model. A big chunk of the standard model is essentially Young-Mills, right? And there are sort of special cases that are well known. So if you take the case of U1, so where the group G is really just the circle, right? Then this is actually classical electrodynamics. Okay, if you write down what it means to be a critical point of that action functional, you find Maxwell's equation. And if you do, if your base space is space-time with the Minkowski metric, right? And so then the critical points of the action functional is basically solutions to a wave equation. And so in this case, this is Maxwell's equation, and this curvature tensor is actually the what's that? That's the electromagnetic potential. So, and the one form is the electromagnetic field. And in the case of SU3 or G, that is the theory that's supposed to describe the strong force. Okay. So that's where this comes from. And so now here's the formulation of the Millennium problem. So it says, prove that for any compact simple gauge group G, a non-trivial quantum Young-Mills theory exists on R4 and has mass gap delta bigger than 0. Okay. So, and then there's a second sentence which is a little bit more technical, which basically explains what you actually mean by existing and what does one actually mean by being Young-Mills. How do you decide that you've constructed the right thing? Okay. So let me sort of try to explain these 3 words, which is maybe the 3 words that are operative here. The first one, so non-triviality is mainly somehow about small-scale behavior, in some sense. But, well, sort of bit of both. But in terms of if you wanted to actually prove this, so if you wanted to actually solve the problem, to prove non-triviality, you would mainly have to control what happens at small scales. The existence part really needs you to control both small scale and large scales, and the mass gap is mostly about how the thing behaves at large scales. Okay, so that's some sort of cartoon, if you want, of the different words that sort of appear in this formulation. And so what I want to explain today is mostly about what's been happening here in the last 5 years. And so there are different aspects about, there's sort of different, essentially equivalent ways of interpreting what you mean by existing, or what's actually a quantum field theory. Now there are axioms, so actually the formulation of the problem tells you which are the axioms that need to be verified, right? So they're called the Whiteman axioms. So in some sense, it's kind of clear what are the axioms that need to be verified. But still, there are different ways of thinking about it from the mathematical point of view. So there are different ways of thinking about if you want objects that ultimately satisfy the same kind of axioms. And the way of thinking about it that I want to talk about today is the probabilistic one, obviously, because I'm more of a probabilist. So that's what I'm going to talk about. And there, in a nutshell, you can think of the quantum field theory associated to an action functional, like I just described on the previous slide, as some kind of probability measure on your space of fields that's formally given by e to the minus your action functional times Lebesgue, whatever Lebesgue measure means. Okay. And well, okay, it's not clear whether such a thing, clearly since it's a famous open problem, it's not clear whether such a thing exists. But if it does exist, right, then there's a work from the 70s by Osterwalder and Schrader, who basically said that, well, if you can do that, if you can construct a probability measure on some space of distributions that in some sense can be interpreted as having e to the minus that action functional as its density with respect to Lebesgue measure, then there is basically a way of turning this into a real quantum field theory. Real quantum field theory meaning, you have a Hilbert space, you have a Hamiltonian, you have a unitary evolution, and so on, and you have some observable operators that give you kind of local field observables or something like that. So I don't want to go into, details of how this Osterwalder-Schrader construction goes, but it mainly, as I would say, one of the main assumptions is that your action functional should be local, which it sort of clearly is in this case, in the sense that it's an integral over some function of values and derivatives of the field at that point. Okay, and it doesn't do like double integrals at different points or something like this. Okay, so if you take a local action functional, and then there's a bunch of conditions that your measure needs to satisfy, and it's all very technical, but essentially, this is sort of the main structural assumption is that you have some form of locality. Because the way it's formulated is reflection positivity, but one way of, like the standard way of verifying this is basically it comes from locality. Then you can construct an actual quantum field theory out of this. Okay, so I'm going to just take this for granted. And I say, okay, so the problem becomes construct this measure, and then there's the, okay, and then show that it has some properties, right? There's some properties you need to satisfy for it to be a plausible candidate of the object that you're actually after. Okay. So now so if we now go back to the formulation of the problem, right, there were three things. There was existence, there was non-triviality, and there was mass gap. So how do these get reinterpreted in that kind of probabilistic framework? Existence, well, I wrote some kind of formal expressions like e to the minus action functional times Lebesgue, and of course there's no Lebesgue measure in infinite dimension, right? So that's probably one of the first things you learn in measure theory. Is you can do Lebesgue measure on Rd, and if you try to send d to infinity, it doesn't work, right? Like there's no sigma finite measure on R infinity, which is translation invariant. So what you do is you want to somehow discretize things. You want to, look at measures on some Rn for n very large, and then take limits. So here, what you would do, right? So you would discretize the underlying space. Say you replace your R4 by a chunk of four-dimensional lattice, like a finite chunk of four-dimensional lattice. Now, at every point of the lattice, you attach a copy of your group. And now what's a connection? Well, the connection was a way of kind of lifting paths, right? So it means you look at the edges on your lattice, and then to every edge, you actually associate a group element, and it's the group element that tells you how you kind of rotate things when you traverse that edge. Okay, so then that tells you a way of actually lifting. You have paths, say, in your graph or in your piece of lattice, and then you want to lift it to lattice times copy of the group. You basically need to be given a group element for each edge, right? That tells you how to lift that. And then you can write, there's a discrete version of curvature where you just take, little squares in your lattice, you go around the square, you look at how much you've moved, and that's your sort of discrete curvature. And then you take some way, now that's a finite element of a Lie group. You have to give yourself some kind of a distance from the origin or something like this. And then you sum these up. Right? You take something like this, some kind of discrete version. And so now that's called a lattice gauge theory, this kind of discrete version of such a Young-Mills theory. And now since your space is basically just a finite number of copies of the group G, and G was compact, so it has Haar measure. So you have now a Lebesgue measure, which is simply, finite product of Haar measures on that group. And so you can look at the measure e to the minus that actual functional. Okay, so now that's a perfectly well-defined probability measure, and then you can ask yourself, do you have a limit? As you somehow send the lattice spacing to 0 and, and make your chunk larger and larger. Then there was the question of non-triviality, right? So non-triviality basically means that the limit you should get shouldn't just be a Gaussian thing. Okay, that's basically what it means. And that's really non-trivial. So for example, there's a very closely related field theory, which is more of a toy model, which is called the phi-4 theory, where your action functional, your fields are just scalar valued functions, just real valued functions, and your action functional is integral of gradient phi square plus phi to the 4, which is somewhat similar, right? Because if you look at, if you go back, you see, what does your action functional look like? It's the integral of that quantity squared, right? So that quantity, there's one bit, which is essentially the exterior differential. So that's a bit like a gradient. It's sort of only half of it, right? It's degenerate, but it at least looks a little bit like a gradient. And that gets squared here. And then there is this term, which is quadratic in A, right? And then again, it gets squared here. Right? So if you look at this expression squared, there's going to be a term that looks a bit like a derivative that's squared, and there's a term that looks a bit like a power 4. And of course, there's a cross term as well. So you can take a toy model, which is called the phi-4 theory, where you simply take, gradient phi square plus phi to the 4. That's sort of the simplest cartoon, which is non-trivial in the sense that it's not a quadratic functional. And then if you take that one in 4 dimensions, there's a, famous, quite recent result by Eisenman and Duminy-Coppin, where they showed that there, basically, whichever way you take limits, you put this on a lattice, then you can put constants in front, like you can put a constant here, you can put a constant here, and so on. Like whatever you do, the limits you're going to get are always going to be Gaussian. Okay. So, and the structure here, as we've seen, is very similar to the one that you see in Young-Mills. But there are good reasons to expect that Young-Mills behaves differently from phi-4 in that respect. Okay, so like dimension 4 is really the borderline dimension in the same way as we've seen this morning in the case of the Navier-Stokes equations, dimension 2 was some borderline dimension, right? So we've heard quite a lot this morning about somehow having control of the L2 norm being just about enough in 2 dimensions for Navier-Stokes. So here, the kind of norm that you end up controlling is closer to like some kind of H1 norm, right? Because it's the relevant functional here is this integral of curvature square, which looks more like an H1 norm. And if you do the same sort of power counting or dimensional arguments as we heard this morning about Navier-Stokes, then you find that the critical dimension here is 4 rather than 2. Okay, so that's why dimension 4, if you want, is the most interesting dimension for Young-Mills. And well, dimension 4 is also the critical dimension for this phi-4 theory because it scales in the same way, because somehow the terms look very similar. But if somehow in 4 dimensions, then typically you have somehow logarithms showing up, and things depend very much on kind of the sign of these terms with logarithms showing up. And that seems to be different between phi-4 and Young-Mills. So there is a argument, which is basically called sort of the renormalization group, which tells you that, which somehow suggests that the phi-4 theory at the critical dimension is trivial at large scales, whereas the Young-Mills theory at the critical dimension is trivial at small scales, and that's the thing you want. And then the final word here was mass gap. And of course, on the face of it, it means that there's a spectral gap in the spectrum of the Hamiltonian. But if we go to this kind of probabilistic way of looking at things in terms of measures on spaces of fields, what it really means is that you have some exponential decay of correlations. So that if you basically look at, right, so that you have a random, now your field is supposed to describe some kind of a random connection on this 4-dimensional sort of principal bundle, and you look at what happens sort of there and over there, it should be essentially independent if these 2 regions are sufficiently far. Right? That's basically what the mass gap means. And one way of sort of seeing that, so why does that have anything to do with sort of, if you take the simplest field theory, so that's that's the field theory that describes non-interacting massive particles. Okay. And so that field theory is given by this action functional here, which is a bit like this phi-4, but with a square instead of a power 4. And the mass shows up here as the coefficient in front of that quadratic term. Now this, a measure with density e to the minus that, any reasonable definition of this should give you a Gaussian measure, right? Because it's e to the minus some quadratic expression in the field. Right? And so measures that have e to the minus something quadratic with respect to something like Lebesgue measure, they are Gaussian measures. And then you know that the density of a Gaussian measure is given by e to the minus a quadratic thing, and the matrix that shows up in there is the inverse of the covariance matrix. So it means that the covariance of this thing, this field, is going to be inverse. It's the Green's function of the operator, of this quadratic form. So it's the operator minus Laplacian plus m squared. Okay? And so if you look at the Green's function of minus Laplacian plus m squared, well, there's an explicit formula in terms of whatever Bessel functions or something, but it decays exponentially. Okay? And the rate at which it decays is basically m, okay? Or maybe 1 over m or something. So then if you want, it's by analogy even, you can just say, well, this is what it means to actually have a mass, is that you look at the exponential rate at which correlations decay, and then you take whatever, 1 over that rate or something like this. But you can actually then relate this to, spectrum of the Hamiltonian and stuff. Okay, and then, of course, if you take this point of view that I just gave you, is that there's a related question here, is then, what sort of space should this thing even be a measure on? Because, I started off by saying, well, everything is kind of smooth. But then if you take, whatever, phi-4 or so, or if you even take this free field, right? So like that measure, we can say, we can answer any question we want about that field theory, right? And then if you look at the measure on the space of fields that this generates, it doesn't live on smooth fields. It doesn't even live on functions. right? In particular, it doesn't live on H1 functions, right? So like formulate has density e to the minus this expression with respect to Lebesgue measure, but this expression is not going to be finite, okay? Because if it was, that means that actually Lebesgue measure would exist, right? But we know that Lebesgue measure doesn't exist in infinite dimensions. So these things don't live on, functions for which this action functional is finite. They don't even live on functions. They live actually on distributions, and they live on distributions that are pretty singular. And so now, there's the question, what does it even mean to have a connection, like a distributional connection? Because the point of a connection is to be able to lift curves. But for this, you would want to at least know what the connection does along a curve. And if you take a distribution, well, you can't restrict it to a curve in general, right? So it's actually pretty non-obvious even what would be a reasonable state space for this measure to live on. Yeah? And so why is it particularly hard to kind of construct this Young-Mills measure? So first, there's one major problem, which is the fact that you're interested in dimension 4, and 4 is the critical dimension, which is the one where basically we don't really know how to construct these things, except sometimes in cases where the limit is trivial, like in the result by Eisenman and Duminier-Coppin. Then even if we somehow knew how to do that, there's another problem here, which is that you have this huge symmetry, right? I just argued on the first slide that you have this gauge group, which is all smooth functions from the base space into your group, which acts by some kind of changes of coordinates. And under this action, the action functional didn't change, right? Like the curvature just transformed by conjugation, and then the action functional didn't change at all. And that means that, in some sense, this e to the minus s of a, it's kind of flat in infinitely many directions. And so again, because there's no Lebesgue measure in infinite dimensions, that means that there's no chance on the face of it, actually, of defining a measure of the type e to the minus s of a dA, right? Because it would look like, well, if you look at on each orbit of this infinite dimensional group, s of a is constant on each orbit, right? So like then that density would be the same everywhere on that orbit, which means that, again, it would basically look like Lebesgue measure on each of these orbits, and we know that and these are infinite dimensional, and we know that Lebesgue measure doesn't exist in infinite dimensions, okay? But fortunately, you don't actually have to do this, because for Young-Mills, the only physically relevant observables are the ones that are themselves invariant under the action of this gauge group. Okay? And what this means is that you really only need to construct a measure not on the space of connections, but on the space of kind of equivalence classes of connections under the action of this infinite dimensional group, right? So you want to basically quotient your space of connections by the action of this infinite dimensional group, which is just smooth functions, these kind of changes of coordinates, okay? So the typical example of a physical observable is what's called a Wilson loop, which is exactly what I explained earlier on, is you take a loop in your copy of R4, then you lift it with your connection, you look at how much you've moved, right? You go back to the same fiber after going through the loop, but you go back at a different point of the fiber, you look by how much you've moved, and then you apply a class function to that. For example, take the trace, if it's a matrix group. And that's an example of an observable that's, well, invariant under coordinate changes or under the action of the gauge group. And in fact, every observable can be approximated by functions of these Wilson loops. So, okay, so you really need to somehow find some kind of state space of distributional connections modulo action of this gauge group, and then somehow build some kind of measure of the type e to the minus that action functional on this. And so there was some progress on that kind of program back in the 70s and 80s. So the big milestones there was that first in the 70s, people like, well, there was the result by Glim-Jaffe, but also Feldman before that, and Osterwalder as well, who constructed this phi4 measure, which I mentioned earlier, where you just look at your action functional gradient phi squared plus phi to the 4. They managed to construct that one in dimension 3. Not in in dimension 4, I mentioned that now we know that it's actually trivial, so there isn't really a construction of it. But in dimension 3, it exists. And that was constructed sort of in the 70s. And so then people tried to do something like this for Young-Mills, and there's a series of works by Balaban in particular in the 80s, and also some of them by Federbusch, and then there was a work by Magnan-Rivasseau and Seneor, and they look at a finite volume, not all of R4, but look some kind of like a torus or something like this, and they show that there's some type of small-scale stability, right? So in some sense, they show that things are not too badly behaved at small scales if you kind of send like lattice spacing to 0. The two-dimensional case is special. So in 2 dimensions, these Young-Mills theories are integrable in the sense that you can basically guess an explicit, you see, you have these Wilson loops. Now a Wilson loop, you can view it just as a function from that takes as input a connection. Say you fix the loop, okay? And then it takes as input a connection and it spits out a number, right? Which is the trace of the discrepancy of when you go around the loop. And now, if you build a probability measure on this space of connections, that means that now a Wilson loop is really a random variable, right? And like for every loop, you get a different random variable. And it turns out that you can basically guess a formula for the joint law of these random variables for any number of loops and any shape of loops, smooth loops, okay? So there's essentially an explicit formula that you can guess. You can say if the Young-Mills measure did exist, then it would lead to random variables that have these joint distributions, and you can basically just write them down. Okay? So in that sense, the two-dimensional case is really well understood, but it's because we sort of know the answer. We don't really have to go through the process of constructing things. You can sort of guess the answers. But this recently, somewhat recently, Ilya Sheverev showed that you can actually really realize these. You can find some kind of state space of distributional connections, and you can find a probability measure on that space, which then has the property that, if you look at Wilson loops on finitely many loops, the joint distribution is the correct one. So that's a little bit like the question of, so it's like the difference between describing something by just finite dimensional distributions or describing it really as a probability measure on some, good infinite dimensional space. But then, so more recently, together with AJ Chandra, Ilya, and Hao Shen, so what we've obtained was essentially constructed what's called stochastic quantization for the Young-Mills theory in dimension 2 and 3 in finite volume. Okay, so it's still very, very far from what you want to do, because you'd want to do dimension 4 and you'd want to do infinite volume. But it's at least one small step. And I'm going to explain in a second what this actually means. Okay. And then on the mask out, so this is all on the sort of existence side, right? Or existence and uniqueness, or existence and non-triviality of the theory. And then there's this question of the mass gap, right, which is this sort of exponential decay of correlations. And there's also been some recent results, so there's one result by Hao Shen with the Zhu sisters, where they showed that if you take a lattice gauge theory, so it's like this discrete version of Young-Mills, which I mentioned early on, then under certain conditions, basically, now you have a length scale that's kind of built into the system, which is in some sense the lattice spacing. That means that somewhere there's a parameter. In the sort of the Young-Mills theory, the way it was written, of course, you can say, oh, I could always put like constants, right? I wrote e to the minus s of a. I could have put constants in front of the s of a, and then even in the definition of the curvature, there was one term which was the differential, then there was this quadratic term, I could put constants in front. But these constants, you can always just eliminate them by rescaling, by redefining a to be a multiple of a and rescaling space. So in some sense, I can always get rid of constants, but if you're on a lattice, then you cannot do that. There's still, right, there's actually a constant left. So then there is really a length scale there in the system. And so there what they showed is that if you look at this discrete Young-Mills theory for a gauge group, which is SUN for n large enough, or somewhat equivalently for, you can do basically any fixed n, but then there's the one parameter that's still left needs to be small enough, then there is a mass gap. Okay, but that's really on the discrete theory. And then there's a couple of recent results also there's a result by Kal, Nissim, and Sheffield, and another one by Surav Chatterjee, where they showed that this decay of correlations implies some other property, which is called the area law, which is, in some sense, it's a slightly different version of what you mean by having a mass gap, okay, which is in the way physically more relevant maybe than the decay of correlations. Okay, so there's some results in that direction now. And well, okay, so maybe in the, there's 10 minutes that are left. So I want to maybe just say a few words on these recent results that we obtained together with Ilya, Hao, and AJ on the stochastic quantization of Young-Mills. So what's stochastic quantization? So that was actually proposed by Parisi and Wu in the early 80s, precisely in order to deal with the fact that for gauge theories, remember I just told you that you really want to construct this kind of measure on equivalence classes of connections, where you take connection and then you kind of quotient by the action of this gauge group. And of course, then you get a kind of horrible space, right? I mean, it's kind of difficult to get a handle on the space that you get in that way. What you would like to do is, well, for each of these orbits, just choose one representative, right? And then that would give you kind of a nicer way of looking at that space. And that's what's called gauge fixing in this business. And unfortunately, there's a theorem which says that, well, at least generically, you cannot do this gauge. You cannot globally do gauge fixing for these theories. And so what Parisi and Wu said, well, okay, what you can do is you try to first write down, you introduce a fictitious time, right, which is not the time of your quantum field theory. It's a sort of extra parameter, which you then view as a dynamical variable, but it has nothing to do with physical time. So you introduce this fake time, and then you build a Markov process where the time of the Markov process is that fake time, which has the property that it has, at least formally, you want to guess some kind of Markov process, which has as its invariant measure the measure that you're after. And now that Markov process would somehow diffuse along these gauge orbits, right? And then, of course, it would run across orbits as well, right? And now what you're saying is, well, since I only care about the equivalence classes, what I could do is I could modify that process so that along the gauge orbits, I make it kind of much nicer behaved than it kind of wants to be. And that's then some sort of a soft version of gauge fixing, which then you can do globally. Okay? And so that was sort of Parisi and Wu's original idea, but that was, well, proposed in 81. And basically, well, we didn't have the mathematical tools to do much with this until about 4 or 5 years ago. Right, and so the idea is that you want to construct measure e to the minus s, and in general, like on Rn, the most natural Markov process that has this measure as its invariant measure is a kind of gradient diffusion of this type. So you essentially do like a gradient descent, but you add some noise to it. Okay? So you do some sort of noisy gradient descent, and well, this thing has as its invariant measure this e to the minus s. Okay, and so you just do that in infinite dimensions. So you take your, for s, this Young-Mills action functional. Now can you analyze that process, right? And so if you do that, you found an equation like this. So this is somehow the gradient, if you want, of the Young-Mills functional. And this is kind of annoying because you don't have a Laplacian here, right? There's a d star d, but there's no dd star. And since we're talking about one forms and not scalar, well, d star d is actually degenerate parabolic, right? So you have a term that's sort of like this, and then there's a cubic term and a quadratic term. And so there's this trick, which was actually first introduced, well, it was introduced by de Turck in the context of the Ricci flow, and then by Simon Donaldson in the context of Young-Mills, which is to say exactly this thing. You can add a term to the equation, which is a term that only pushes you in the direction of the gauge orbits. So if you quotient out by the action of the gauge group, that term shouldn't do anything, right? But it turns out that you can add a term like this in such a way that it kills this extra term and gives you a real Laplacian. Okay, so then at least you get an equation that looks like some kind of nice parabolic PDE. Right, so if you do that, okay, so that was sort of the picture here, is you sort of at every point, you have these gauge orbits, which are all infinite dimensional. And so now at every point you add an additional drift that kind of moves in the direction of these gauge orbits in such a way that the equation that you get is nicer. Okay. And then the question is, can you give a meaning to that equation? And does it still, so you want, in the end, you would want a Markov process which is gauge invariant in the sense that, if you take two different initial conditions on the same orbit, and then you run the solutions with these two different initial conditions, then you would want to get the same solutions if you quotient by the gauge group, right? So you want the thing to be well defined in that sense, in law at least. And so now, okay, so the equation that you get, the structure of the equation is the following, right? So it's a heat equation. There's a quadratic term that really comes from the cross term in the action functional. And then there's a kind of cubic term which comes from the, right? So there was a quartic term in the action functional, and it comes from taking the functional derivative of that, then you get something cubic. So there's a cubic term, a quadratic term, and there's this heat equation term. And like one way, and then you have this noise term here, which I wrote as psi, which is space-time white noise. It's essentially something like independent random variables at every point in space and time. It's some sort of a random distribution with a correlation that's delta function in space and delta function in time. Okay? And then here, already at the level of that equation, we can also see that dimension 4 is special. So what makes dimension 4 special here is that if you look at somehow like regularity of space-time white noise, it's minus dimension plus 2 over 2. The reason the dimension over 2 You can kind of see it from a simple scaling argument. The extra +2 comes because of the extra time direction, and it counts double basically because that one time derivative has to balance up with this Laplacian. So there's a kind of, in terms of your scaling, you want to scale it in a way so it counts double. We saw exactly the same in the context of the Navier-Stokes equation this morning. And then it means that the solution to this equation, if it's somehow reasonably behaved, then it should have regularity 2 better, because it's like a heat equation. You gain 2 derivatives. So it should have, so A should have regularity 2 minus d over 2, which is still negative. So if dimension is bigger than 2, which shows that it's still a distribution. And then if anything, that cubic term should in some sense have regularity 3 times that. And now if you take d equal 4, here you get a -3, here you get a -1, and then this is again a -3. And if you look at this term, you also get a -3. So in dimension 4, it's exactly the dimension in which all of the terms in this equation sort of balance up. So formally, the equation is scale invariant under the scaling similar to the scaling we've seen for Navier-Stokes this morning. So the equation is formally scale invariant. So formally, every single term in the equation should be similarly strong. Okay? And that's the reason why it's very difficult to analyze. Right? Like it looks like a semilinear equation, but it's really not, because the nonlinear terms are just as strong, even at small scales, as the linear part of the equation. But in dimensions less than 4, in some sense, the nonlinearity is weaker than the linear part of the equation. Okay? And so then here you can, but still, how do you give a meaning to this equation, right? Because all the regularities were negative, even in dimension 3, it's all negative. So none of these terms have a meaning, right? Like they're sort of quadratic and cubic terms of distributions that don't have a meaning a priori. So you still need to somehow discretize the thing and pass to the limit. So you could, for example, just smoothen the thing out, try to pass to the limit. And it turns out, so by now we have this kind of general machinery which allows you to basically prove theorems that say that these kind of equations do have limits when you do that. Okay? So it's a completely general machinery, provided that it's subcritical, which means provided that at very small scales, the nonlinearities count less than the linear part, which exactly means dimension strictly less than 4 here. Yeah. But then you kind of smoothen it out, and you need to somehow renormalize these equations, which in this case means you have to add an extra term of this type with constants that possibly diverge in order to get a limit. And then it looks like you're in trouble, because there are very few equations. We want to have this gauge invariance, right? And which the Yang-Mills equations have. But if you add this extra term, that breaks it, right? Because A doesn't transform in the right way. We saw that it doesn't transform like a tensor. You get this additional term in it. So this is no longer gauge invariant. But in some sense, smoothing out the noise also breaks it. And so then you can still hope that maybe it's broken in 2 ways that kind of cancel each other out. Okay? And that was basically our contribution there. Which was to say that both in 2 dimensions and in 3 dimensions, there's kind of a miracle happening here, which is that these 2 different ways of breaking gauge invariance, as you send epsilon to 0, they cancel out, and you really get a limit, which is a Markov process that has, again, this gauge invariance property. So you really get a Markov process on some space of gauge orbits. And in 2 dimensions, in fact, you have a very clean result. You can really describe a nice space of distributional connections for which, for example, the Wilson loops are continuous functionals on that space and things like this. And then even there's a recent result by Ilya and Howe, which showed that in 2 dimensions, if you do that, you can actually prove that the process you get in this way, this Markov process, has an invariant measure, and the invariant measure has exactly the finite loop distributions, which is the one that was guessed by people back in the 90s or something. Okay, so you get really the right object in that sense. So in 2 dimensions, we had an object which was obtained by guessing finite dimensional distributions. And so here we can recover it in a sort of more systematic way. We know that we get the right object. But the construction also works in 3D. But in 3D, it's still only local in time. So we get a process which might possibly blow up. Okay, so here it is. Well, okay, so I think I've run out of time. I see that Alison is sort of getting nervous, so maybe I'll stop here. And thank you very much.